let's get started. Okay, so just to kind of recap what we were doing last time, this last page was essentially a pretty good comprehensive summary of what we were talking about, and then also the governing equations for this unit. So since we're looking at open systems now, so we're doing control volume analysis, that of course means that we have mass flow in and out of our system. And so we need to take into account conservation of mass in that case, as well as conservation of energy. So I have those two forms of the equation here, and we're going to make use of that today as well. Okay, so the first thing we're going to talk about is modeling control volumes at steady state. All right, so just a reminder, steady state means that nothing is changing with respect to time. Or another way of writing that is that time derivatives are zero. All right. This is an important kind of category of flows and assumption that we can make because many engineering devices that we'll care about as engineers are going to operate for long periods of time over the same working conditions and are therefore classified as steady flow devices. All right, and most of the analysis that we're going to do, we're going to be making the assumption that the flow is steady. And so a steady flow is characterized by the following. So no properties within the control volume or the CV change with time. They can, of course, vary with space though. So just if you say something doesn't change with respect to time, it could change with respect to space. So keep that in mind. Okay. And so that means that because of this, total energy, volume, and mass in the control volume remains constant. All right, because any change with those things with respect to time is going to be zero. In addition, we have no properties changing with time at the boundaries of the control volume. So the fluid properties at inlets or exits remain the same. And we also usually assume that the properties at an opening are uniform. So at an inlet or an exit are uniform. So things like inlet velocity or exit velocity, we're going to assume that's a uniform velocity at the inlet and the exit. If you're an ME student and you take 3500, you will find that we learn how to do what happens if that's not the case. So that's more of a fluids problem. And then third, oh wait, actually one more note. So inlet properties don't need to be equal to the exit properties. So just be careful there. So they're both not changing with respect to time, but they could change relative to each other. Okay. Okay. Next we have that the heat and work interactions. So heat and work interactions between a steady flow system and its surroundings do not change with time. So this means that Q dot of our control volume and W dot of our control volume are constant. And keep in mind, all of these statements that I'm making only apply if we are talking about a steady state system, okay? So as soon as you can make the argument that nothing is changing with respect to time, then you can go ahead and make all of these assumptions, okay? All right. In reality, of course, the properties of control volumes that we consider to be steady state do technically vary with time. And typically, this is due to turbulent fluctuations. So I'm going to constrain myself to this tiny little space to tell you about turbulence just real quick. It's a personal favorite topic of mine. That's what my research is in. So I could talk about it for hours and hours and hours, but I will not. So turbulence is essentially chaos in a fluid flow. And what that means is that if we were to have the opposite of turbulent flow, that is called laminar. So that is like very smooth and organized and predictable flow, which if we were to look at something like the velocity versus time for a laminar flow, it would do something like this. Very boring, am I right? Whereas if we have turbulence, turbulence will do something like this. So there's going to be some chaotic behavior in there, but you'll notice that it's kind of floating around the same average behavior. And so one circumstance we could have is this. We could alternately have turbulence that's even a bit crazier. So these amplitudes could be even bigger. And it's doing something over a regular interval, okay? Okay, so if this is what's happening in reality, which typically it is, it's kind of tricky to get laminar flow in most systems. So turbulence is a real thing that's going on. We can still assume steady state if our fluctuations are small and the average is constant. Okay. When we're analyzing flow devices, we're often going to simplify the conservation of energy equations by assuming some terms are small enough to be neglected. I find that this kind of strategy comes up in lots of engineering classes. So that's an important one to recognize. So it's really important to, first of all, know what governing equations you want to use, and then also be smart about the simplifications that you make. Okay. So in the next few little bits here, we're going to talk about when we can and cannot make certain simplifications that are going to be very convenient for us. For example, simplifying that Q dot for the control volume is approximately equal to 0. This is okay to do if the following is true. So the heat transfer term so Q dot CV is our heat transfer term. So if this term is small relative to other energy transfers, across the boundary. I've already kind of left this vague though, right? What does small mean? Anybody have any ideas? What would constitute small relative to other terms? It's hard to say, right? So this is very much going to depend on, your engineering application. So if you're designing a part that goes on the ISS, small is probably going to have to be like a fraction of a percent, maybe smaller than that, right? If you are designing a giant heat pump for like an industrial pool or something, then maybe 1% is okay, right? But it depends on the application. Okay. The second condition that makes this assumption okay is that the outer surface of the control volume is insulated. All right. The third one is that the temperature difference between the control volume and its surroundings is small. And the reason why we can use that argument to say that Q dot is effectively zero is because heat transfer is always driven by a difference in temperature, right? So we don't have heat flowing when there's not a temperature difference. So if the temperature between your control volume that you're trying to analyze and the surroundings is very close, then that amount of heat transfer will be minimal. It might still exist, but it should be small. Okay. And then last, we have if the fluid passes through the control volume so quickly that there's not enough time for significant heat transfer to occur, or the outer surface area is too small for effective heat transfer. So essentially conditions for which heat transfer is not conducive. So things like fast flow or small surface area. Does that make sense? So if you were thinking about water flowing through a tube that's cold and it's being exposed to like a hot exterior gas, for example, if your water is going really, really fast, it's not going to get heated very well by that outside air. And also if the surface area that the water is exposed to air is really small, that's also not going to be super effective at heat transfer either. Okay. Okay. So these are all the reasons why we might make a valid argument that Q dot is zero. We might also want to argue that W dot is zero as well, or is effectively zero. All right. So this happens when there's no rotating shafts. No displacements of the boundary. No electrical effects. Or other work mechanisms. I think we all feel pretty comfortable with identifying where and what work is present in a system based on what I've seen so far of you guys in homework and in exam. So kind of same old as what we've been doing before. So be careful for anything that's being output or input into the system that you're given in the problem. So like electrical work, shaft work, all that good stuff. And then be super cautious about not forgetting about the boundary work, right? So if our volume is changing, we're going to have to take into account boundary work, right? Okay. We also typically, and we've been doing this in class already, the change in kinetic and potential energy and PE of the fluid entering and exiting our control volume is often neglected. This is typically because either there is no change in velocity or elevation, or the changes that there are so small relative to the other terms in the energy equation that we neglect them. So this is because of either no changes in V or Z, or changes are small relative to other terms. Again, I have used this term small. It's very vague. It again depends on your application. Okay, so just be mindful of that. So what we're going to do is we are going to consider the values of kinetic and potential energy per unit mass for a few cases. So we're going to consider KE and PE per unit mass. All right, so our first one is we have a velocity of 45 meters per second. All right, so we want to find our KE per mass, which I'm going to write as a lower KE because it's specific. All right, and so this is just mv squared over 2 divided by m. So we just have 1/2 v squared, right? So we have our 45 meters per second squared divided by 2 times some unit conversion stuff. So 1 kilogram per meter per second squared is a Newton. And then I just need a teeny bit more space here. All right, it's not meant to be. And then 1 Newton times meter is a joule. Okay, so we have, canceling out here, we have meters squared cancels with these 2 meters in the denominator. And then we have per second squared goes away. And then Newton and Newton cancel. So we have joules per kilogram left over, right? So when we carry out this arithmetic, we get 1012.5 joules per kilogram, which is 1.01 kilojoule per kilogram. Okay. So relative to some of the other energy terms, if you remember from like the exam, for example, internal energy was in units of kilojoules per kilogram. We were looking at numbers that were on the order of magnitude of like 2000, right? So this 1 kilojoule per kilogram, not huge relative to that, right? Okay, let's do another example. Now let's look at a velocity of 140 meters per second. So here we have our kinetic energy per mass is 1/2 v squared, or 140 meters per second squared divided by 2. And we already know from before that this is joules per kilogram. And so what we get here is 9.8 kilojoules per kilogram. Okay, so a bit bigger. Our third example is going to be potential energy. So if we have an elevation of 100 meters, our specific potential energy is potential energy divided by m. So we have mgz divided by m, which just leaves us with gz. All right, so we have 9.81 meters per second squared times 100 meters. And our conversion for the units here is the following. So we have 1 kilogram meter per second squared is a Newton, and then 1 joule is 1 Newton meter. Okay, so our Newtons go away. This meter and this meter is 1 over meter squared, and then we have 2 meters in the numerator, so we can get rid of that. And then we can also get rid of the per second squared. So we have joules per kilogram. So this gives us 981 joules per kilogram, or 0.981 kilojoules per kilogram. And then last but not least, let's make this 10 times bigger. So if Z is 1,000 meters, then we have our specific potential energy is G times Z, which is 9.81 times 1,000. And this is joules per kilogram, which gives us 9.81 kilojoules per kilogram. Okay. All right, so relative to some of the terms that we are used to looking at for our energy equations, these values are not super large. Even though we're looking at velocities that are fairly aggressive here, 45 meters per second and 140 meters per second is cooking, okay? And then, in my opinion, 1,000 meters and 100 meters are also pretty large changes in relative elevation, okay? Okay. Oh, and I guess I'll just write this down. I've kind of said this. So if you compare to the enthalpy of steam, so these are values that range from about 2,000 to 5,000 kilojoules per kilogram. All right, so PE and KE are often neglected. Does everybody feel convinced? Okay, great. Okay, now that we've done some discussion of steady state flows and kind of what terms we can neglect and when, let's talk about some specific engineering devices that are steady flow devices. All right. So for each of the devices that we're going to talk about, we're going to list the most common assumptions made for analyzing each device. And many of the devices that we're going to consider operate steadily, which is why we're talking about them right now. And they also have one inlet and one exit. So under those conditions, conservation of mass is fairly simple now. So our original equation is the time rate of change of mass in our control volume is equal to the sum of m dot at the inlet minus the sum of m dot at the exits. All right, since we are considering a steady flow, that means that this goes to 0. And then since we have one inlet and one outlet, so our one inlet just becomes m dot I. and then our one exit just becomes m dot e. So we can drop this sum. So what we end up with is the following. So we have 0 is equal to m dot in minus m dot out, e, exit. Okay. All right. And our conservation of energy becomes the following. So our full conservation of energy is the time rate of change of the total energy in our control volume, which is equal to Q dot of our control volume minus W dot of our control volume plus M dot times the quantity HI minus HE plus 1/2 VI squared minus VE squared plus G times ZI minus ZE. All right, so this is delta H, this is delta KE, and this is delta PE. All right, since it's still steady, we can get rid of this term on the left-hand side. And then the rest of the terms we'll see, right? Any questions so far? Okay. All right, so the first device we're going to talk about is nozzles and diffusers. They're essentially the same device, but they operate opposite directions from one another, okay? So nozzles and diffusers are commonly used in fun things like jet engines, rockets, spacecraft, and sadly garden hoses. This list cracks me up. It's so sad to end with just garden hoses. But yes, they do have nozzles. The nozzle is a device that increases the velocity of the flow at the expense of pressure. So as velocity goes up, pressure goes down. And then a diffuser is a device that increases the pressure of a fluid at the expense of velocity. So by slowing the fluid down. This is another thing that comes up quite a bit in 3500 if you take that class. But if you remember from lab 1, where we talked about the Bernoulli equation, so that was basically conservation of energy and it involved pressure and velocity. Because of the way that conservation of energy is structured, if you increase your velocity, pressure has to go down. Okay, so they're connected in that way. Okay. The cross-sectional area of a nozzle decreases in the flow direction. For subsonic flows, and then increases for supersonic flows, and then the reverse is true for diffusers. I don't expect you to remember the stuff about sonic flows. That's actually a topic that's in intermediate fluid mechanics, which is an elective class if you're an ME student. So you can look forward to that if you're interested in that sort of thing. But just kind of a note here. Okay. So this picture here has a nozzle and a diffuser connected in the same device. This is a wind tunnel. All right. So wind tunnels are used to do lots of things like characterize the aerodynamics of a vehicle, for example. We have one in the fluids lab, which is right next door to the thermo lab. And you'll get a chance to try that out in a lab in 3500 if you're an ME student. I promise I'm not trying to plug ME right now. Okay, so let's talk about the relative importance of terms in the energy equation. So our handy dandy energy equation is given to us right there. And we want to simplify this in the case of a nozzle or diffuser. So we want to simplify for nozzles and diffusers. Okay, so first of all, we have steady flow. So this means that dE dt of the control volume is going to be 0. So we can always get rid of that guy. And the other simplification that we're going to make is we are going to assume that the heat transfer from the control volume is approximately 0 unless told otherwise. Generally, the argument would be that either we're in a situation where the temperature difference is not very large relative to what's inside the nozzle or diffuser and the surroundings, or we can make an argument that the fluid flow is very fast, so there's not going to be a lot of heat transfer going on. Okay, if you have to take it into account, I would tell you. Okay, W dot. So our work term is going to be 0. So if you look at this system, there's no spinning shafts here. There's no electrical inputs. This is a device that has rigid boundaries. So the boundaries aren't moving. We don't have boundary work here. So that's just kind of by definition of what this device is our work is going to be 0. Okay. What about the change in kinetic energy? What do we think? Can we neglect that? No? I thought I saw someone shake their head no. You would be right if you said no. So the whole point of this is to change the velocity, right? If we're using a nozzle, we want the velocity to be much higher at the outlet. So this in general is not 0 because that's kind of the point of this device, right? All right, so we're trying to change the velocity either higher or lower depending on what we want to do with the pressure. So we can't ignore that. What about potential energy? I'll bring you back to the picture. Any ideas? So this is a horizontally oriented nozzle and diffuser. So definitely there's no changes in potential energy for this one because it's, vertical displacement is the same at the inlet and the exit. Even if you had it oriented the other way, generally speaking, a nozzle or a diffuser is not going to be so tall that that would be an important thing to consider. Okay, so we will assume that this is generally 0 as well. Okay. Any questions in general about nozzles or diffusers? Okay, let's do an example then. Or do you want to do a break first? You want to do break and then example? Press on, do the example? Okay. All right. So we have air at 80 kilopascals and 127 degrees Celsius enters an adiabatic diffuser steadily at a rate of 6,000 kilograms per hour and leaves at 100 kPa. The velocity of the airstream is decreased from 230 to 30 meters per second as it passes through the diffuser. You may assume that the air behaves as an ideal gas. Find the temperature of the air and the exit area of the diffuser. Okay? All right, so let's mark up this problem with useful things and assumptions that are already spelled out for us. So one that I'm going to highlight here is adiabatic. Does anybody remember what adiabatic means? So adiabatic means no heat transfer. So this means Q dot is equal to 0. Okay. We also are given that this is steady. So this means that our time derivatives are equal to 0. And then we're given a bunch of information about the flow that we're going to write down in just a second. But we're also told one more thing that I wanted to highlight here, we're going to assume that the air behaves as an ideal gas. So that's going to be useful to us too. Okay, so I'm going to first draw myself a picture. So we have a diffuser. A diffuser means that its inlet area is smaller than its exit area. So we have our inlet and our exit that are going to look like this. It's adiabatic, so I'm going to draw little hash marks around it because that's generally in pictures how we show that there's something that's insulated. All right, and we have our inlet condition over here. So we have pressure, temperature, m dot, and V given to us. So our inlet pressure is 80 kPa. Our inlet temperature is 127 degrees C. M dot is 6,000 kilograms per hour. Keep in mind we have this per hour, so we're going to have to be careful about units. And then our velocity at the inlet is 230 meters per second. Okay. And then at the outlet, we have the pressure at the exit is 100 kPa. And our velocity at the exit is 30 meters per second. But we don't know what the temperature at the exit is, and we don't know what the area at the exit is. All right, so we want to find those things. All right, our control volume is just going to be the contents of our diffuser. So this is our control volume. So our second step is draw the CV and write assumptions. So we have a couple of assumptions that we've already kind of called out in the problem text. So we're assuming that there's no heat transfer because they told us it was adiabatic. We're going to assume that it's steady, which means our time derivatives go to 0. And we're going to assume that we can treat this as an ideal gas. So far, so good? Okay. So the next thing that we want to do is write down our governing equations. Equations. All right, there we go. We have 3 that we're going to want to keep track of. So our first one is we have the ideal gas law. Right, so we're treating our gas as an ideal gas, so we should write that down. So we have P times specific volume is equal to R times T. That's our ideal gas law. So I'll call that equation A. We're also going to need conservation of mass, maybe. And we also need conservation of energy. All right, so conservation of mass is dm dt for the control volume is equal to the sum of the inlet mass flow rates minus the sum of the exit mass flow rates. All right, and then our conservation of energy is the following. So we have the time rate of change of the total energy in the control volume is equal to Q dot minus W dot plus the sum of the inlet energy flows. So we have enthalpy plus 1/2 VI squared. This is our kinetic energy and our potential energy. And then we subtract off our outlet energy flows, which looks the same, but they all have the exit subscript. All right, so we have enthalpy kinetic energy, and potential energy. Okay. Okay, so let's simplify our equations. Based on our simplifying assumptions that we put into. All right. So it's adiabatic, so we can get rid of the Q dot term, right? So I'm going to do that first. We have steady flow, so I can get rid of both of these dt terms. The ideal gas, we already wrote down the ideal gas law. One other thing that we want to keep track of here is that we have one inlet and one exit, right? So it's not really an assumption, it's just kind of a part of the problem. So we have one inlet and one exit. So that means I can get rid of these summations, all right? Because it's a sum over one thing, right? Are there any other assumptions we should add to this list? Are there any other terms that we can potentially get rid of? Say again? Yeah, so we're going to neglect potential energy. I need a different color. Love it. Get rid of those. Anything else? Yeah, we're going to get rid of work too. Have I done all the colors? No, not blue. So no work. So we can get rid of that. All right. So our simplified equations are much simpler. So we still have our ideal gas law, PV is equal to RT. And then conservation of mass is just 0 is equal to m dot in minus m dot out, which just means that m dot in is equal to m dot out. And I'm just going to call that m dot because we're given m dot, right? It is the same. All right, and then conservation of energy is 0 is equal to m dot hi plus 1/2 vi squared minus m dot he plus 1/2 ve squared. Is m dot 0? It's like 6,000, right? So we can divide this equation, both sides of it, by m dot and just get rid of it, right? So that means that we have hi plus 1/2 vi squared is equal to he plus 1/2 ve squared. Okay. Any questions so far on the simplification, the assumptions? Yeah. So we don't have any, well, we don't have any information to even say what it might be, but this is just a horizontally aligned thing. So we're assuming that it's like vertical displacement from left to right is the same. Yeah. Oh, down here. So I just divided both sides by m dot. I can write that. Does that make sense? Okay. Other questions? Okay, great. All right, so let's remind ourselves what we're trying to figure out. So we want to find temperature at the exit, and we also want to find area at the exit. All right. Any suggestions on which one we should do first? I would suggest that we find the temperature first. So we can use ideal gas law to find the temperature. Sorry, I'm just gonna add another page here. There shouldn't be too much more work if you want to work in the margin underneath the table there, if you've run out. Okay, so first we're going to find TE, and we're going to use the ideal gas law. All right, and we have that P E VE is equal to R times TE, right? So I can solve this equation for TE, and I have that this is PE VE over R. We can look up R from a table because we know that it's air. We're given the pressure, but we don't know VE yet, right? So we don't know this yet. Any ideas on how we might find that? So I will give you a small hint. Oops. So hint, HE only depends on TE, right? So if we can find HE, then we can find TE using the air table, right? Okay, so to find HE, we will use conservation of mass, or sorry, conservation of energy. So I'm going to solve equation C for HE. And we have HE is equal to HI plus 1/2 VI squared minus 1/2 VE squared. All right. And we know VI, VE, and we can find HI because we have all the other information about the inlet. So we have VE, we have VI. So let's find HI. So we're going to use table A21 to find, oops, HI. Okay, so let's remind ourselves at the inlet we have 80 kPa of pressure, 127 degrees C of temperature. So we're going to go to our table. Keep in mind, we have temperature in degrees C, but this table is in Kelvin, right? So we're going to have to do a bit of conversion. C as 100 not degrees, 400 Kelvin. All right. So we're going to go down to our 400 Kelvin, which means that HI 400 E. So we're going to plug all that information in, and we have 400.98 kilojoules per kilogram plus 1/2 VI squared, which is 230 meters per second, squared minus 1/2 VE, which is 30 meters per second squared, which gives us a value of 426.98 kilojoules per kilogram. I did not show it to you again, but the conversion to get from meters per second squared to kilojoules per kilogram was the same as like when we looked at the values for kinetic energy and potential energy just a little bit ago. Okay. Okay, good. So now we have HE. So that means that we can use that same table to find TE. All right. And we're probably going to have to interpolate, right? So we have, we want to find TE, and we know that our enthalpy at E is 426.98 kilojoules per kilogram. Can anybody look at the table and tell me which ones we should interpolate between? Yes, great. Thank you. So we're going to interpolate between 420 and 430. So I've got 420 and 430. And then I'm also going to pop in here our enthalpy values, which are, can someone read them to me so I don't have to go back and forth? What's the 420 enthalpy? Okay. Point what? 4.3. Great. Thank you. Okay. So let's interpolate to find TE. So TE minus 420 divided by 430 minus 420 is equal to 426.98 minus 421.26 divided by 431.43 minus 421.26. All right, and so we do this calculation and we get that TE is 425.6 Kelvin. All right, so we sorted that out. Now all we want to do is find A, right? So last we need to find AE. So at the exit, we have that M dot E is equal to AE VE divided by specific volume of E. All right, this is earlier in the note packet. This is just the definition of mass flow rate, right? Okay, so we still need to have VE. But if you remember when we had our ideal gas law, we didn't have TE or VE, but now we have TE, so we can use that to solve for VE, right? So we can use the ideal gas law, which gives us that VE is equal to RTE over PE. All right, R is, this is 0.287 kilojoules per kilogram Kelvin. All right, so this means that we can solve this as the following. So we have 0.287 kilojoules per kilogram K times our temperature at the exit, which is 425.6 Kelvin, divided by the pressure at the exit, which is 100 kPa. And we get that VE is 1.22 meters cubed per kilogram. Okay, so now we can go back to this equation and solve for AE. So AE is equal to m dot E VE divided by the velocity at the exit. We've got our 6,000 kilograms per hour, and then 1 hour is 3,600 seconds. So let's just take care of that conversion straight away. Times VE, which is 1.22 meters cubed per kilogram, divided by 30 meters per second. That's the velocity at our exit. All right, and so our hours cancel out, per seconds cancel, kilograms cancel, and then one of our meters goes away. So we end up with meters squared, which is good because we wanted an area, right? So we have that AE is equal to 0.068 meters squared. Do you regret not taking the break before this? Do you guys want to do a quick break? Okay. Okay, you guys ready? All right. Before we go into this next one, I wanted to just check in with you guys. Does the pace of the class feel okay? Am I going too fast? It's okay? Okay. If it ever feels too fast, feel free to tell me because I have a tendency to write and talk fast. So I'm not offended. Okay. All right. So we talked about nozzles and diffusers. Now we're going to talk about turbines, compressors, and pumps. And so this is a class of devices that either generate work output or require work input. And they all often involve rotating shafts. All right, so a turbine is a device in which work is developed as a result of a gas or a liquid passing through blades, a set of blades attached to a shaft that is free to rotate. In steam, gas, or hydroelectric power plants, the device that drives the electric motor is the turbine. And then in the case of steam or gas turbines, superheated vapor or gas enters the turbine and expands to a lower exit pressure as work is output. All right, in the case of hydraulic turbines, so these are things like in a dam, water falling through a propeller causes a shaft to rotate, thus producing work output. Okay, so this picture I have on the left here, this is an axial flow turbine. And then the one on the right is a hydraulic turbine in a dam. All right, and generally speaking, these will kind of be cartoonized as the following sort of sketch. So we will have flow in and out. So we have pressure in, temperature in, pressure at the exit, temperature at the exit, where generally the pressure at the exit is less than pressure at the input. And then we have work coming out. Make sense? Okay. Compressors, as well as fans and pumps, are devices that are used to increase the pressure of a fluid. All require work to be input, but are different in terms of the task, not the taste, the task that they perform. So fans are going to increase the pressure of a gas slightly, but they're mainly used to move a gas around, as anybody who has used a fan probably already knows. A compressor is used to increase the pressure substantially. Of a gas. And then a pump is similar to a compressor, but it's going to handle liquids instead of gases. Okay. In these pictures, I have a rotating compressor. So these are all rotating compressors. These are axial and centrifugal. And then this one over here is a reciprocating compressor. For pumps, the kind of general schematic looks like this. So we have it's usually drawn as a circle. We have an inlet and an exit, and then work is coming in to that system. So we have PI, TI, PE, TE, where PE is greater than PI. We're wanting to increase the pressure. And then for a compressor, so this is a pump. The compressor, we draw in a similar shape to the turbine, but it's facing the other way around. Okay, so we have PI, TI, PE, TE, work goes in, and then we have PE is greater than PI. Any questions so far? Okay. So if we assume one inlet and one outlet, we can get rid of the summation signs on our conservation of energy equation. So we just have the one inlet set of terms and then the one outlet set of terms, which I have in this equation here. But now we want to talk about kind of the relative importance of the terms in this equation. So we're going to still assume that these are generally steady devices. So if you remember, we're still in the section where we're talking about steady flow devices. So this is still steady. So our left-hand side goes to 0. The next assumption that we'll typically make is that the heat transfer term is approximately 0. So we can say this if Q dot CV is small, or we're saying that Q dot CV is assumed to be small compared to W dot CV. But obviously include Q dot terms if told to do so. If you're not told, then you can assume the Q dot's small, okay? What about W dot? Can we get rid of that? No, right? So that's pretty important. Turbines, the work is output. All right, so we have W dot CV is greater than 0. And which means then that W dot CV is equal to W dot out. And then for compressors, fans, and pumps, work is input, which means the sign changes. So work of our CV is less than 0. So W dot CV is equal to minus W dot in. All right. Do we have feelings about the change in kinetic energy? So we can usually say that this is about 0. So this is generally small. And even in turbines where velocity changes quite a bit, it's still quite a bit smaller than the changes in enthalpy, just like how we saw at the beginning of class. Okay, so that's still the case here. Potential energy, we're also going to generally say is about 0, except for a couple of important cases. So one exception to this would be a hydraulic turbine where the flow is driven by elevation changes. Like at Niagara Falls. All right, probably not going to neglect potential energy in that case. And then also problems where you're sizing a pump to raise a fluid to a certain height. So you would have a hard time calculating what that final height is if you've neglected changes in potential energy, right? So generally we can say it's 0 unless we have one of these two circumstances. Any questions on these assumptions? So always keep work, always get rid of heat transfer unless told otherwise. Pretty much always get rid of kinetic energy, and then same with potential energy except for 2 exceptions, okay? Okay, let's do an example. Which hopefully we can at least start it. Maybe we can finish it, we'll see. I believe in us, okay. All right, so in rural areas, water is often extracted from underground pumps. So this is when you have a well. Consider an underground water source whose free surface is 200 feet below ground level. The diameter of the pipe is, the liquid water is to be raised 15 feet above the ground by a pump. The diameter of the pipe is 6 inches at the inlet and at the exit, neglecting any heat interaction with the surroundings and frictional heating effects. Determine the power input to the pump required for a steady flow of water at a rate of 240 gallons per minute. Assume that the temperature of the water remains constant and equal to 65 degrees Fahrenheit, and that the inlet and exit pressures are both atmospheric. Whew, okay. So let's, I'm going to kind of highlight some things on this drawing, like getting rid of the things that are wrong at the moment, which is all of them. Okay, so the picture is fine, the numbers were not. Okay, so we have that we have an underground water source whose free surface is 200 feet below ground level. Here's our ground level. So this dimension here is our 200 feet. The liquid water is to be raised 15 feet above the ground. So we want to raise it this distance, which is 15 feet above the ground, by a pump, which is shown here. So there's our pump. The diameter of the pipe is 6 inches at the inlet and the exit. So we have this diameter is 6 inches, and then this diameter is also 6 inches. Neglecting any heat interaction with the surroundings. So this means that Q dot for the control volume is going to be 0, right? And frictional heating effects. Determine the power input to the pump. So we want to find W dot CV. For a steady flow of water, so steady flow, we're going to mark that up too, at a rate of 240 gallons per minute. So this 240 gallons per minute is V dot at the exit is 240 gallons per minute. The temperature of the water is going to remain constant and equal to 65. So we have TE is equal to 65 degrees Fahrenheit, and then TI is also 65 degrees Fahrenheit. And the pressures are both atmospheric. So we have PE is P atmosphere, and then PI is P atmosphere. Okay. All right. So let's write down our governing equations because we've already got our picture here. So we're going to use conservation of mass and conservation of energy. Last time we also had ideal gas law, but this is water, right? So we're not going to use ideal gas law. So we've got conservation of mass, which is dm dt is equal to the sum of the mass flow rates at the inlets minus the sum of the mass flow rates at the exits. Okay. And then we also have conservation of energy. So we have dE dt is equal to Q dot CV minus W dot CV plus M dot HI minus HE plus 1/2 VI squared minus VE squared plus G times ZI minus ZE. Okay. Let's write down our simplifications. Or our simplifying assumptions. We've got a couple. So we have that this is steady. That was given to us in the problem. We have Q dot of our CV is equal to 0. Any other assumptions that we should make? Can we do anything about kinetic or potential energy or work? So I would suggest that we get rid of kinetic energy. Okay. So we're going to neglect kinetic energy. We're going to assume that it's very small relative to the change in enthalpy. All right, so I can get rid of this term. Potential energy we probably ought to keep, right? Because this is one of those special circumstances where we're trying to figure out a sizing of a pump to pump water up a certain distance, right? So we need to keep our potential energy in here in order to use all the information that's given to us and satisfy our requirements. So we'll keep that. And work obviously is what we're trying to find, so we got to keep that as well. We know that Q dot is 0. That was already given to us. And we know that this is a steady system, so we can get rid of our time derivatives. The only other thing that I'm going to mark off here is my summations here, because we only have one inlet, one outlet. Right? Okay. So let's write out our simplified equations. So we have that 0 is equal to m dot in minus m dot out. And then we have that for energy, 0 is equal to minus W dot plus M dot HI minus HE plus M dot G ZI minus ZE. Okay, we want to find this. So I'm going to solve for it. So I have that W dot is equal to M dot HI minus HE plus M dot G ZI minus ZE. Okay. Do we have anything available to us yet for this equation? We know gravity. And we're given distances. So we know Z, or we can sort out ZI and ZE. Does anybody have any ideas about what ZI would be? This was kind of a trick question. That was mean of me. So we need to, when we're looking at elevation differences, we need to figure out where is Z equals 0. And it doesn't matter where you put Z equals 0 is, as long as you're consistent when you measure ZI and ZE. Okay? Okay. So where should we put Z equals 0? Any suggestions? Some places are more convenient than others. Yes, Leo. I love it. That's where I would put it too. Right here. Okay, great. So if that's where our inlet is, or I gave it away. If that's where Z equals 0 is, then our inlet Z value is 0, right? And then our exit is 215 feet above that. Does that make sense? Yes.
So would this negate any turning back or priming?
Yeah, so we're like grossly simplifying this here. Yeah, so we're gonna assume very idealized pump conditions for this, but it's a fair question. Other questions? Okay, all right, so we've got ZE and ZI and we have G, but we don't yet have M dot and we don't have HI or HE. I think M dot is the easier one to solve first. Does anything in the problem, is anything given to us in the problem that's close to M dot? We're given volume flow rate, right? So volume flow rate is related to mass flow rate. So we're given V dot, but M dot is equal to V dot divided by the specific volume, right? All right, so we're using liquid water. So we will assume that V is equal to, or is approximately equal to VF at 65 degrees Fahrenheit. All right, so we're gonna assume that we can use the properties of water at the saturated liquid state at 65 degrees Fahrenheit, which I conveniently have the table for you here. Okay, so we have a line for 65. So this is our VF that we're going to use. And then we also need enthalpy, right? So we want to use this value of enthalpy as well. Okay, so this is 0.01604 cubic feet per pound of mass, which means that we can find M dot is 240 gallons per minute. Hold on to your socks. We're going to do a bunch of conversions. Don't worry. This is, and then divided by 0.01604 cubic feet per pound of mass. All right, so I need to convert this gallons per minute into cubic feet per second. All right, so I'm going to do the following conversion. So I'm going to multiply this by 7.48 gallons are in each cubic foot. And I have that there are 60 seconds in a minute. All right, and so when I do this, then I can get rid of the minutes. I can get rid of the gallons. I can get rid of the cubic feet. And I end up with 33.34 pounds of mass per second. Okay. All righty. Okay, so we now have M dot, so that's good, which is right here. The last piece that we need is HI minus HE. So we are going to use our specific heat equation for this. So HI minus HE is equal to C times TI minus TE plus our specific volume times PI minus PE. All right, we already said that PI and PE are equivalent. They're both equal to P atmosphere. So this goes away since PI equals PE equals P atmosphere, right? And we also have this term goes away, right? Because we said the temperature at the inlet and the exit is the same. So our change in enthalpy is 0. Okay. So I'm going to put a little star here, and then we say that this is 0 C star. All right, so that means that W dot is equal to M dot G ZI minus ZE, which is equal to all right, there's unit conversions. Hang on just one second. I don't want to shortchange you on the unit conversion. So we have 33.34 pounds of mass per second times 32.2 feet per second squared times minus 215 feet, which gives us minus 13 horsepower. All right, so this means that it's work input into the system, which we would expect, right? You have to put work into a pump to drive the water up in elevation. So that checks out. I knew we could do it. With a few minutes to spare. Does anyone have questions on this problem? Yes. So it is a compressed liquid, but we're just assuming, we're just going to use the approximation that it's the saturation. Remember how we approximated a compressed liquid for the saturation curve? Yeah. Yeah. Yep. No, nope, nope, nope. So if you put, if this was Z equals 0, then you would have, we had ZI minus ZE, right? So ZI is minus 200, yep, and then ZE is plus 15. I'm sorry, so it's minus the positive 15. There we go. Yep.